Hello, my name is Dr. Edgars Butanovs, and I'm from Thin Films Laboratory of Institute of Solid State Physics of University of Latvia. Today I will give you a brief introduction to thin film characterization techniques. In this lecture I will give you a very brief overview of different composition and structural characterization methods, different surface morphology methods, and a very little bit about characterization methods of optical properties of thin films. And then I'll give you some very brief tips about your process development. So, what is a thin film? So it's a thin coating on a supporting substrate. It can be either solid or flexible substrate, and it can be very thin, even few nanometers thick, few atoms thick, or a bit thicker, as well as it can be deposited on very small substrates or very large substrates, such as large area glass. So a definition of how thin is a thin film typically is defined as a fractions from a few nanometers or a monolayer to several micrometers. In thin film science, the questions to answer is how does a thin film grow? Then how to deposit a thin film, how to control thin film properties, which deposition method best to choose for your desired applications, and where these thin films can be used. So, in thin film science, it deals with different type of investigations. So first of all, fabrication, characterization, and then applications. It provides understanding of the relationship between the preparation, structure, and properties of the films. So this is of critical, as you see in this schematic. So depending on your target application, you will need to select the optimal processing method, and it will be interlinked together with the structure and properties of this. So in the end, characterization is in the middle of all of this. So between your application properties, device performance, and its structure. So what do we want to know about our thin film, which we have just deposited? So first of all, how does the sample look like? This can be divided in different scales, in macroscopic scale, in microscopic scale, or on atomic scale. Each of this provides us different information about our sample. Then we want to know what is the internal structure of the sample, whether it's amorphous, crystalline, polycrystalline. Then we want to know what is the sample made of. So it means its elemental composition, impurities, chemical state, and some other things. And then, mainly for applications, we are interested in what are the functional properties of our sample. So it could be electrical properties, optical, thermal, mechanical, magnetic. But this part will be out of the scope of this current lecture. So then there are two questions. What do we want to know, or what do we need to know? So no single technique will give all the information we want. And we always need to use at least several techniques to characterize the sample. Yes. So, and what do we really need to know? So do we need to know the information from our sample, or just some selected areas? Do we want to know the information from the surface, or we want to know what's the composition or structure inside the film? Then we need to decide how high resolution do we need to do our measurements with. So it can be very high resolution or small resolution, or do we need to know about very small concentrations of elements, or we don't care about that. As well as we need to be careful to select destructive techniques if we need to do some more characterization afterwards. So those are typically stay for the last. Okay, let's move to some of the most common methods of composition and structure characterization. So how to probe matter? We can use different, let's say, physical probes or physical phenomena, how to probe matter. One of the most commonly used is electromagnetic radiation. However, we can also use electrons, ions, neutrons, neutral atoms, or touching with some kind of nanoscale probe. From this electromagnetic radiation, one of the most common things is to use X-rays. So X-rays are used commonly to probe material composition. So if we irradiate our sample with X-rays, So the X-rays can either be transmitted through unaffected, there can be photoelectric absorption, there can be relay scattering, and there can be Compton scattering. And each of this, except transmitted unaffected, can give us some information about our sample. So let's see what happens if we analyze the characteristic secondary X-rays. So if we plot them by energy, we can identify the characteristic peaks of individual elements, and this gives us information about the elemental composition of the samples. Usually it's on the scale of few millimeters, so it gives you information about the relatively larger area. And on simple tabletop tools, usually you can detect down to a few atomic percentage. Usually elements, you can measure elements starting from beryllium, but usually there is weak signal below sodium. So the next method we can use is X-ray photoelectron spectroscopy. In this method, we analyze the detected photo-emitted electrons by energy. And that gives us information on the elemental composition of the samples. Usually it can be down to even 30 microns. However, the signal depth usually is 10 nanometers, so it's a surface-sensitive technique. In good tools, you can detect down to around 0.5% atomic percent, and depth profiling is possible when using argon milling. And in this method, you can quantify nearly all elements except hydrogen and helium. What is beneficial of this method, you can study chemical states. So in this method, photoelectrons are sensitive to chemicals, different chemical shifts, which depends on the chemical compounds of the specific element. For instance, as you can see here in the middle figure, in tantalum oxide or tantalum selenide, they have shifted photoelectron, these 4F peaks. And that gives us information about the chemical state of this compound. Furthermore, another method is it's not related to X-rays, but still used for composition characterization. It's secondary ion mass spectroscopy, or SIMS. In this method, you bombard the sample with primary ion beams, and you analyze the mass-charge ratio of the emitted secondary ions. And in this case, you can, by measuring this mass and charge ratio and plotting in the spectrum, you again can identify specific ions. It can be used both for inorganic compounds and as well as larger organic molecules. It gives us elemental composition, and the benefit of this method, it's very, very sensitive, and it can detect down to species to 1 part per billion. And usually with this ion beam milling, you can do depth profiling. The benefit of this method is you can also detect hydrogen, so it's very important for semiconductor industry to see how pure your semiconductor films are. In semiconductor SIMS measurements, it's very common to prepare so-called SIMS stacks, where you prepare sequential layers of your film with different either doping or alloying, and then when you do the depth profiling, you can see the change in the concentration in each layer, and that gives you very valuable information how to fine-tune your semiconductor growth process. The next method we'll talk about is Raman spectroscopy. If you illuminate your sample with a light, let's say visible light, you can get inelastic scattering from the molecular vibrations or phonons in your sample. And this shift can be used to study the vibrational modes in your material, and these vibrational modes are your structural fingerprint. So you can use this for compound identification, since it's unique for different compounds with different bond strengths or orientations. And in some cases, you can also identify phase, different polymorphs. They're kind of qualitatively characterize their crystallinity, and as well as other effects. A very well-known method to use for thin film characterization is X-ray diffraction. In this case, there is elastic scattering of X-rays, and depending on the Bragg's law, there will be specific constructive interference in some cases, which depends at specific angles and depends on the crystal symmetry, lattice spacings, etc. And if you measure this angular distribution of this diffraction, you can obtain so-called Bragg's peaks, and then with this X-ray diffractogram, you can use either calculations of your crystal structure or international databases to identify crystalline compounds in your film, since it's a unique fingerprint which you're measuring. And if you do further fitting of your obtained X-ray diffractogram, you can determine as well crystalline size, lattice strain as well. And it works well for polycrystalline thin film samples. However, when you start to get some texture or your films are perfectly monocrystalline, you will only obtain few peaks, and then you can do some other measurements. And in that case, powder diffraction can be used just for let's say, phase identification. Since X-rays penetrate several microns into the sample, by using grazing incidence angle beam, so a beam at very low angle, you can get a better signal of your thin films and get less signal from your substrate. Especially it's useful if it's a monocrystalline substrate. And then by varying detector position, again, you can measure the characteristic Bragg peaks and examine the XRD in plane of the film. You can also perform X-ray reflectivity measurements at these very low angles. When you get total external reflection, the onset of X-rays entering the films will depend on the density of the film, as well as interference from the top and bottom of your layer of the films produces oscillations. So you can measure thickness as well for your thin film. Usually it needs to be below, let's say, 1 micron thick film. As well, you can get some information about the roughness, since it attenuates the signal. If you perform so-called rocking curve, when you fix the detector position but rock your sample around the Bragg angle, you can determine the real width of your peaks, and this is strongly related to the thin film quality, texture, dislocation concentration, grain size, etc. So the narrower your peak in the rocking curve is, the higher the crystallinity will be. So it will be less textured and with less structural defects. Lastly, you can also rotate your sample in plane, and this will give you in-plane symmetry, which you can use to obtain heteroepitaxial relationship to the substrate. As well as in more advanced case, you can do reciprocal space mapping to give you very detailed information about the strain in your multi-layer thin films, or epitaxial thin films. Let's move to some more direct methods, such as transmission electron microscopy. We can study directly the inner crystalline structure of the thin films with a TEM, which allows to see atomic planes and therefore measure the interlayer distance, determine some stacking relationships, distinguish grains, grain boundaries, as well as dislocations, and in some very advanced tools, also point defects. Usually the sample thickness needs to be below 100 nanometers to penetrate the sample and get some information. So a specific thin film lamella preparation needs to be performed, and it's usually done in a scanning electron microscope focused ion beam tool. Using gallium ions to etch out so-called lamella and lifting it out with a manipulator probe and then welding it to the TEM grid and then doing rough polishing gives you usually a nice quality thin lamella of your thin film cross-section, which can be then imaged in a TEM. In TEM, you can obtain atomic resolution of your thin film, and then, as I already said before, distinguish different properties of your thin film cross-section. So whether it's ground boundaries, some defects, and phase identification as well. Usually in the TEM tools, there's also a selected area electron diffraction measurement possibility, and that can be used for phase identification. Since similarly as with X-ray diffraction, electron beam also diffracts in your crystal, and by measuring the diffraction pattern, you can estimate your phase and orientation as well. And furthermore, usually tools also have so-called energy dispersive X-ray spectroscopy detector inside the tool, and this, similarly to X-ray fluorescence discussed before, gives us information about the elements in our sample. You can either obtain information from a single point or perform mapping over your lamella or your crystalline lattice. There are many other techniques you can use, of course, such as Auger electron spectroscopy, for backscattering spectroscopy, Fourier transform infrared spectroscopy, and many others. However, these are out of the scope of this lecture. You can also use synchrotron radiation, which give you much higher resolution of the analysis. However, of course, you need to apply for the beam time in the these synchrotron facilities. Okay, let's move towards the other methods for surface morphology characterization. So how can we take a look at the thin films? Either we can take a look by our eye, however, that's usually not very useful. We can use optical microscopy, but it has some limitation due to diffraction of light. And then we can use either electron microscopes or scanning probe microscopies, and those we will discuss further in the following slides. Optical microscopy is useful for quick investigation of surface features, and usually it can be used to determine whether you have some large defects in your film, such as cracks, delamination, or maybe some dust contamination, if that's important. However, to get higher resolution, we need to use electrons to illuminate our sample, and the best tool for imaging conductive samples is scanning electron microscopy. You can get much higher resolution, up to magnifications of 500,000, so resolution can be even down below 1 nanometer. And in this case, you get electron intensity map, which is counts per point. We can use two different detectors. We can use backscattered electron image to show chemical segregation, since backscattering is very dependent on the atomic number of Z. For instance, it's useful if you have some alloyed films with elements with different atomic numbers. So then you have a good contrast between this distribution. Or you can use secondary electron image, which is very good for topography, since it gives much higher contrast for different surface features. It can be used to study grain features in your thin films, as well as perform cross-section imaging, since usually you can obtain either different contrast for different element films or compound films, as well as, you can approximately determine the grain size or grain features or growth mechanisms, let's say. And then, similarly, as I mentioned in TEM, also SEM tools usually have this EDX tool for element identification and mapping, and usually you can detect elements starting from boron, and as well you can perform mapping to identify where in your sample, especially if it's not uniform, where are different elements segregated. To perform a higher resolution, more detailed surface analysis, typically atomic force microscopy is used. It uses a tip with a size of few nanometers fixed on a cantilever, which is scanning, oscillating above your sample, and due to electrostatic force, the induced bending is measured in the cantilever, and the feedback is given back to the piezo stage, and it constructs the surface image. What is beneficial with this tool, first of all, is the high lateral resolution, but it also gives the real topography as well as vertical resolution, which was not possible in SEM imaging, since it's just a projection of the surface. So here you get a detailed image of different grain features, their roughness, etc. And roughness is one of the main properties typically measured for thin films to see whether it's a very smooth conformal epitaxial growth or it's typically polycrystalline film, or maybe you have some protruding grains. As well as it can be used for height profiling of some surface features, or if you grow, for instance, some 2D materials, it can be done to measure the thickness of that. You can also use AFM in a different other modes, such as conductive mode or magnetic mode. You need to use specific tips for that. And this, in each case, gives you information either about the conductivity of your samples. For instance, if you have some segregated grains which are more conductive than the other parts of the film, or in magnetic imaging mode, you can also see magnetic domains. And with more advanced tools, you can measure also piezo response. So atomic force microscope is not only a tool for just simple surface morphology measurements, but can be used to study advanced physical phenomena of the films. For more detailed characterization of very atomically smooth films, you can use scanning tunneling microscopy. It's based on the tunneling effect between the very, very sharp tip of the microscope and the surface. And the applied bias between the two allows the electrons to tunnel through the vacuum between them. And the resulting tunneling current is basically the local density of states of the sample. And it usually is displayed in an image form. So it can be used to characterize atomically smooth and conductive surface to image density of states distribution. And that gives us information, for instance, on some specific point defects and some terraces and atomically sharp defects. So this is typically used for very high quality material or for some fundamental studies of different materials and their defects. For simple cases, for thickness measurements, we can use contact profilometry. It uses a stylus which is scanned over the sample in a contact mode. And it's a very useful and quick tool to determine the thickness of film, especially if you have some step on the film due to some masking. And that gives us, that we can commonly and very quickly use to determine the sample thickness of your thin film. Let's move to the last section of this lecture, the optical properties. So here I'll mainly talk about only two methods which are related to the band gap estimation or some defect estimation. So first method is photoluminescence spectroscopy. In photoluminescence, photon is emitted due to a recombination of an optically created electron pair. So in semiconductors, photoluminescence usually occurs if the photon excites the electron from the valence band to the conduction band. So it means that the energy must be equal or higher than the material band gap. And this is important. And this radiative recombination, which we are measuring, it occurs at energies close to the edge of the band gap. So it can be used to approximately estimate the band gap, as well as it can be preceded by non-radiative photon emission process. So, in photoluminescence spectroscopy for direct bandgap semiconductors, these band edges are located in the same position in the momentum space, so energy and momentum is conserved when a photon is emitted. However, in indirect bandgap, there needs to be emission or absorption of a phonon to conserve the momentum, and typically that leads to less efficient photoluminescence in such materials. So photoluminescence we can use to estimate optical band gap, so that's the near band emission, as well as we can study optically active defects such as deep level emission. And in this example of the famous material zinc oxide, you can nicely see the different bands of both band emission or defect emission. For direct optical property measurement, you can use UV-Vis infrared spectrophotometry. So in this case, you measure transmittance and or reflectance through your sample. And in some cases, you can also measure light scattering and absorbance. So what do? You need a thin film or a double-side polished substrate, which has a wider bandgap than your thin film. You measure the transmittance and reflectance through all the spectrum. which your tool allows, and then using either a tau plot method or Kubel-Kamunck approach, you can estimate optical band gap from the onset of the fundamental absorption. Okay, let's move to the final remarks. So there, as you saw, there are many techniques to choose from. I only discussed the very popular ones. However, there are still many advanced techniques and specific techniques for different applications. The selection strongly depends on the target application and quality requirements. So for some simpler applications which requires less quality, you can use simple tabletop tools. However, for very advanced, let's say, semiconductor thin films, you will need to use a variety of advanced tools as well. So when you're developing a new thin film deposition process, usually start from simpler and faster techniques, which gives the most information, such as elemental composition, structure, and chemistry, and then move to more detailed and complex methods to fine-tune your deposition process, such as film smoothness, structure, and point defects. All right, thank you for your attention.